Up to now, we've actually been focused on one-dimensional waves, and the best example of that is going to be a wave on a string. However, many waves that occur in the real world are going to be two- and three-dimensional. So one way to think about that is that if I'm speaking in the center of a room, the sound waves that my voice is creating actually are spreading out into the entire room. They're not just going in a straight line. If I drop a rock in a pond, there's actually a circular wave that spreads out. Hence, we need to think a little bit about two- and three-dimensional waves, and really the biggest difference is going to be how we represent them. So what we need to do, instead of just drawing a sine wave, we need to now show this in two or three dimensions. We can't really draw this in three dimensions very well, so we're going to stick to two dimensions. But keep in mind that even though these look like circles, these could be, for instance, the cross sections through spheres. So three-dimensional waves are usually going to have nice symmetries, so you can use a two-dimensional view to represent it. What we do to represent a wave in two dimensions, like this case, is that we draw what are called wave fronts. So the circle here represents every spot where the wave is at its crest or its peak. And so notice that you have concentric circles, so they're coming from the source, which we would assume is the very center. And then the distance between the circles represents your wavelength. So hopefully this is clear. Again, what we're trying to do is take that sinusoidal function, and if I kind of draw my line, we then have a peak here. It goes down and up. I'm not very good at drawing this. We have a peak here, down and up, another peak. And so every time we have a circle, we should have a peak that's up. So just as we know that the distance between two peaks is our wavelength, we then know that the distance between these circles is our wavelength. So if we have a circular wave, that implies that it is going out in every direction equally. And a fancy term we use for radiating outwards in every direction is isotropic, or isotropically. So isotropic waves means that it's going to start at one point and then go out in concentric spheres. So in this case, our velocity is not in one direction, but we can still talk about a consistent wave speed. So normally we don't talk about wave velocity, we just talk about wave speed. So keep that in mind that whenever we're drawing circles, we do mean the circle to be the peak, and this is going to be really helpful when we talk about interference in two dimensions. Now, a second type of wave that's going to occur that isn't a circle or a sphere is going to be what's called a plane wave. And this is going to be relevant when we talk about electromagnetic waves. Now, plane waves are a little bit tricky because, again, we can't really visualize them in three dimensions. But now there's actually going to be a surface. That's what these gray rectangles that you see at an angle are. And the surface cuts through where the wave is at a peak. Now, in this case, you see that we have a position here and we have displacement, right? So again, that's the wavy part of our wave in the vertical direction, but then we have a second direction, which you could imagine calling, for instance, y. So the idea being, instead of a one-dimensional wave, you're now stacking up many waves in this y direction that all then have peaks that align. But we wouldn't actually just show individual waves, it's literally everywhere on this surface in space has a peak. And again, this can happen in three dimensions, but that's really hard to visualize, so we're not going to worry too much about that. But mathematically, this can be pretty useful to think about. So now, when would we actually have plane waves? When is this going to occur? Now, occasionally you can make something that looks sort of like a plane wave, but that's pretty hard to do. So one example would be if I have a really big speaker and I'm just looking at this volume here. If the whole speaker is going back and forth at once, that's going to make something that looks like a plane wave right here. But if I look, for instance, way out here, it's going to start to look more like spherical waves or circular waves. So plane waves is something that we usually actually approximate to. It's hard to create perfect ones. So you get plane waves either when you're close to something really big generating your wave, which doesn't happen often, or you're very, very far away from your source. And the reason for that is, again, in this case, when you have a central source, you get the circular or spherical wave, and you can imagine zooming in and you see that these look almost parallel. Now, obviously there's some curvature, but as you get further and further away, the radius increases such that the curvature is even smaller. So once you're really, really far away, you don't see the curvature. So plane waves can happen if you're far away from something that still is nominally creating circular waves. So a really good example of that would actually be the sun. That if we were thinking about waves coming away from the sun, they are actually going out in a spherical symmetry. But once you're on Earth, they're all kind of coming at us from the same direction. So it would look more like a plane wave in that case. So plane waves are very much a simplification, but it's a very helpful one in many situations.